NASA has committed roughly $20 billion to building a permanent base at the south pole of the Moon. The entire reason for putting it there, rather than somewhere easier to land, is a supply of water ice believed to be frozen into craters that have never seen sunlight. That water has never been measured. Not from the ground, not once, not by anybody. Every figure you have heard came from orbit, from inference, or from the one time we threw a rocket into a crater and photographed the dust. Both missions America built to go and check were cancelled, one of them after the hardware was finished. In a matter of days, somebody else's machine launches to take the measurement instead, and whatever number comes back decides whether any of this was ever possible. If you want to follow this properly, hit like and subscribe to the Skylab. Then tell me in the comments where you're watching from, and whether you think that base ever gets built. Now let's get into it. Part 1. The places the Sun has never reached. At the bottom of the Moon there are floors of craters that have not seen sunlight since before anything on Earth had a spine. That is not a figure of speech. It is a straightforward consequence of geometry. And it is the reason that a few square kilometres of grey rubble, at the southern end of a world we stopped visiting more than half a century ago, have quietly become the most contested territory off this planet. To understand why, you have to start with a number that almost nobody outside planetary science ever hears. The Earth is tilted. Our axis leans over by roughly 23.5 degrees, and that lean is the reason we have seasons, the reason the Sun climbs high in July and skulks along the horizon in December. The Moon does not do that. The Moon's axis is tilted by about 1.5 degrees. It stands almost perfectly upright in its orbit. For most of the Moon that hardly matters, but at the poles it changes everything. When your axis is upright, the Sun at your poles never rises far above the horizon. It circles the rim of the sky, low and flat, casting shadows that stretch for kilometres and never sweep away. And if you happen to be standing on the floor of a deep crater near one of those poles, the wall of that crater blocks the Sun permanently. Not for a season, not for a lunar night. Permanently, in the full sense of the word, for as long as the crater and the tilt have both existed. Planetary scientists call these places permanently shadowed regions. The shorthand in the literature is PSRs, and the estimates for how long some of them have been dark run into the billions of years. Now here is the part that turns a geometric curiosity into the central question of human spaceflight. Darkness on the Moon is not just an absence of light, it is an absence of heat. There is no atmosphere to move warmth around, no wind, no ocean, no weather of any kind. A patch of lunar surface in sunlight can climb well above the boiling point of water. A patch of lunar surface that has never seen sunlight has nothing to warm it except the faint trickle of heat leaking up from the Moon's interior and the occasional glancing scatter of light off a nearby rim. Those floors sit among the coldest surfaces ever measured anywhere in the solar system. Colder than Pluto. And a place that cold does something specific to anything that wanders into it. It stops it. Think of it as a trap with no door and no bait. A single molecule of water arriving at the Moon by any route at all, riding in on a comet delivered by an asteroid, forged out of hydrogen from the solar wind reacting with oxygen locked in the rock. That molecule hops. It absorbs a little energy. It lifts off the surface. It travels. It lands somewhere else. On the sunlit Moon, that process ends quickly and badly. Ultraviolet light breaks the molecule apart, or it simply gains enough energy to leave for good, and within hours it is gone. But if that molecule happens to land inside a permanently shadowed region, it stops hopping. There is no energy to lift it again. It freezes where it sits, and it stays there, and then another one arrives. And another. Over a span of time that dwarfs the entire history of complex life on Earth, the trap fills. That is the theory anyway, which brings us to the thing this entire video is actually about. The closest anyone has ever come to taking a sample from one of those craters was in 2009, when NASA deliberately crashed the spent upper stage of a rocket into one at roughly 9,000 kilometers per hour and photographed the dust that came up. That is not a joke, and it is not an exaggeration. That impact is still, 17 years later, the single most direct piece of evidence we have. The total amount of water it revealed from that one violent event was about 155 kilograms, 342 pounds, roughly what you would find in a large domestic hot water tank. That is the foundation. That is the ground floor of everything that follows. Every plan for a lunar base, every architecture for a fuel depot, every serious proposal for a permanent human presence on another world rests on a resource whose total measured quantity, at any single location, is a plume of debris from a deliberate collision. Nobody has ever put an instrument on the ground inside one of those craters and asked it directly how much is there. In about 11 days, someone is going to try. Before we get to who and how and why, it is not who you would expect. It is worth understanding just how much terrain we are talking about, because the popular image of this is usually wrong. People tend to picture a single spectacular hole in the ground, a dark pit with a glittering lake of ice at the bottom. The reality is stranger and much more fragmented. The lunar South Pole is not one shadowed crater. It is a landscape of thousands of separate cold traps, nested inside each other at every scale you care to look at. At the largest end, there are crater floors tens of kilometers across, permanently dark, deep enough that the terrain around them functions like the wall of a stadium. Inside those, there are smaller craters within the shadow, each with its own deeper and colder floor. And below that, down at the scale of a few meters, there are pockets of permanent shadow behind boulders and inside small depressions that never catch the low-angle sun. Some estimates put the total permanently shadowed area near the lunar South Pole in the tens of thousands of square kilometers when you account for all of it. Others put the useful, genuinely ancient, genuinely cold fraction far lower. That disagreement is itself part of the problem we're going to keep running into. The terrain has one more property, and this is the property that makes it valuable rather than merely interesting. The same topography that creates permanent darkness creates something close to permanent daylight right next to it. Think about what it takes to make a shadow that never moves. You need high ground casting it, and high ground near a lunar pole standing above the surrounding terrain with the sun circling low around the horizon catches sunlight for an extraordinary fraction of the lunar year. Some polar peaks and crater rims are lit for well over 80% of the time, and a handful of specific spots do better than that. In a place where the standard day-night cycle runs about 14 Earth days of light, followed by 14 Earth days of brutal darkness, a location with near-continuous sunlight is not a convenience. It is the difference between a mission that survives and a mission that freezes solid. So the lunar South Pole offers a combination that exists almost nowhere else in the inner solar system. Power on the high ground, preserved volatiles in the low ground, and the distance between them, in some places, is a walk. One crater in particular sits at the centre of all of this, and you're going to hear its name repeatedly from here on. Shackleton, named for the polar explorer who famously never reached the pole he set out for, which is either an unfortunate omen or a very good joke depending on your temperament. Shackleton sits almost exactly at the lunar South Pole. Its rim catches sunlight for a very high fraction of the lunar year. Its floor has never been lit at any point in the history of the solar system. That is the terrain. Now here is why it matters more than any other real estate off this planet, and I want to be precise about this because the reason is not sentimental. There are only two places in the entire inner solar system where volatile compounds, water, and the other light molecules that living things and rocket engines both need, can survive at the surface indefinitely. One is the polar regions of Mercury. The other is the polar regions of the Moon. Everywhere else they are stripped away by sunlight, by the solar wind, by heat, by time. Mars has ice, but Mars is a separate and far more expensive problem. The asteroids have water, but they are further away and harder to reach. The Moon's poles are the only accessible bank. And the thing that everyone building toward that bank has quietly agreed not to dwell on is that nobody has counted what is inside it. This is the central thread of everything that follows, so let me state it as plainly as I can. $20 billion of American lunar architecture, an entire Chinese crewed program, and a growing commercial industry are all oriented toward a resource whose quantity, depth, physical form and extractability have never once been measured on the ground. The number that everything depends on does not exist. It has been inferred, modelled, estimated, argued about and put into presentations. It has never been taken. We have built the plan before we did the survey. Now, I want to be scrupulously fair here, because there is a version of this story that overstates things, and I have no interest in telling it. The evidence that hydrogen is concentrated at the lunar poles is genuinely strong. It comes from multiple independent instruments, on multiple spacecraft, from multiple countries, over more than 2 decades. Nobody serious disputes it. There is something there. The dispute, the actual live, unresolved scientific dispute, is about what form it takes and whether it can be used. And those are not small details. They are the entire question. A crater floor with ice grains scattered thinly through the top few meters of soil is a resource you could scoop and heat. A crater floor with the same total mass of water locked into a hard, cemented layer under a meter of dust is a mining operation requiring machinery nobody has built. A crater floor with a delicate surface frost a few molecules thick is, functionally, nothing at all. Same amount of water. 3 completely different answers to the question of whether human beings can live up there, and we cannot tell which one we are looking at from here. There is a reason this is going to feel unsatisfying as we work through the evidence over the next stretch, and the reason is that every single measurement we have was taken from a distance, through a fundamental obstacle. You cannot photograph the inside of a permanently shadowed crater with a conventional camera, because photography requires light, and there is no light. You cannot measure the composition of its surface with a standard spectrometer for the same reason. Every technique that works beautifully everywhere else on the moon runs into a wall at the exact boundary where the interesting terrain begins. So the scientific community has spent 30 years being extraordinarily clever about workarounds. They have bounced radar off crater floors and argued about what the echoes mean. They have counted neutrons leaking out of the regolith and worked backwards to hydrogen. They have imaged crater interiors by the light of the stars and by sunlight scattering off the opposite wall. They have, on one memorable occasion, thrown a rocket at one and taken pictures of the debris. Every one of those techniques is genuine, careful, published science, and every one of them produces an inference rather than a measurement. 3 machines were built to close that gap, to go to the surface, get inside the shadow and take the number directly. 2 of them are not going. Part 2. Everything we think we know came from hitting it. On the 9th of October 2009, a spent Centaur rocket stage weighing more than 2 tons was falling toward the lunar South Pole, and a small spacecraft was chasing it down. The mission was called L-Cross, and its design is worth understanding in detail, because it tells you something about how desperate the measurement problem is. NASA could not see inside Cabeus crater. Cabeus is permanently shadowed, near the lunar South Pole, and it had been identified through years of orbital data as one of the most promising cold traps on the Moon. There was no way to look inside it, so they decided to make it come out. Here is how the mission actually worked, step by step, because the elegance of it gets lost when people summarize it as NASA crashed something into the Moon. The launch delivered 2 objects on the same trajectory. The first was the Centaur upper stage, the spent booster, now serving as a purpose-built impactor. The second was the shepherding spacecraft trailing behind it, carrying 9 instruments and a radio. The Centaur went in first, striking the floor of Cabeus at roughly 2.5 kilometers per second and excavating a crater about 20 meters across. The impact threw a plume of debris up out of the permanent shadow and into sunlight, where it could be seen, and then, about 4 minutes later, the shepherding spacecraft flew directly through that plume. Not near it, through it. Its instruments sampled the debris in flight, measuring the spectrum of what had been thrown up, transmitting continuously, and then it hit the floor of Cabeus itself and was destroyed. The whole mission was designed around a 4-minute window that ended in the deliberate destruction of the spacecraft that was doing the measuring. That is how badly we wanted to see inside one crater. The result, after months of analysis, was the number I mentioned earlier. Roughly 155 kilograms of water vapor and water ice, observed within the field of view of the instruments as the plume rose, 342 pounds. I want to be careful about what that number means, because it gets misused constantly in both directions. It is not the amount of water in Cabeus crater. Nobody thinks that. It is the amount of water that a single impact happened to throw up into a specific region of space, where a specific instrument happened to be looking during a window of a few minutes. Depending on how you model the impact, how deep it dug, how much of the excavated material went where, what fraction of the plume the instruments actually sampled, you can back out wildly different estimates for the concentration of water in the soil, and people have. The L-Cross data has been remodeled, reanalyzed and re-argued for well over a decade, with new papers still appearing in the planetary science journals years after the event. That continued reanalysis is itself the tell. When a single 4-minute observation from 2009 is still carrying that much interpretive weight in 2026, it is not because the observation was so definitive, it is because we have not managed to get anything better. We covered this a little while back in the video about the rocket stage that hit the moon, and the point stands even more strongly here. Impact has become our instrument of last resort at the lunar poles. In 2009 we did it on purpose, with a chase vehicle and a plan. Since then we have done it accidentally, repeatedly, with dead spacecraft and abandoned boosters, and each time a small community of scientists scrambles to point whatever telescopes they can at the flash. That is not a research program. That is opportunism forced on us by the fact that we cannot see into the dark. So what else do we actually have? This is worth walking through carefully, because the strength of the overall case is genuinely good, and the weakness of each individual link is genuinely real, and those two things are both true at once. Start with neutrons. In 2010, an instrument aboard NASA's Lunar Reconnaissance Orbiter called LEND, the Lunar Exploration Neutron Detector, identified concentrations of hydrogen in Cabeus and in Shoemaker Crater, both permanently shadowed, both near the South Pole. This is one of the most cited results in the whole field, and the technique behind it is beautiful. Here is the mechanism, one step at a time. Cosmic rays constantly bombard the moon. When they strike the regolith, they knock neutrons loose from atomic nuclei, and those neutrons go bouncing around inside the top meter or so of soil before some of them escape back into space. Now, when a neutron collides with a heavy nucleus, silicon, iron, magnesium, the ordinary stuff of lunar rock, it bounces off with most of its energy intact, like a marble hitting a bowling ball. But when a neutron collides with a hydrogen nucleus, which is a single proton with almost exactly the same mass as the neutron itself, it transfers a huge fraction of its energy in one hit, like a cue ball striking another cue ball dead on. So hydrogen slows neutrons down, and an instrument in orbit counting the energy spectrum of neutrons leaking out of the lunar surface will see a distinctive suppression wherever hydrogen is concentrated below. Count the neutrons, and you can map the hydrogen without ever seeing the ground. It is genuinely clever. And now watch what happens when you try to turn that map into a statement about water. The instrument measures neutrons. From the neutrons you infer hydrogen. From hydrogen you would like to infer water. But hydrogen at the lunar surface can be several different things, and neutron spectroscopy cannot tell them apart. It could be water ice, which is what everyone hopes. It could be hydroxyl, a single oxygen bonded to a single hydrogen, chemically interesting but far harder to extract as usable water. It could be hydrogen implanted directly into the top layer of grains by the solar wind, which has been blasting protons into the lunar surface continuously for billions of years. It could be hydrogen chemically bound inside minerals, locked in the crystal structure, effectively unavailable. 4 possibilities, 1 measurement, no way to separate them from orbit, and then there are the resolution limits, which are worse than most coverage admits. Orbital neutron spectroscopy integrates over a large footprint. We are talking tens of kilometers across in the standard configuration, which means a single data point can be smearing together a genuinely rich deposit and a barren plain and reporting the average. It also only sees the top meter or so of soil, because that is as far as the escaping neutrons come from. Whatever is below, that is invisible. So the honest translation of the LEND result is this. There is more hydrogen in some permanently shadowed craters than in the surrounding terrain, distributed somewhere within a footprint of tens of kilometers in the top meter in a chemical form nobody can determine remotely. That is the strongest orbital evidence we have, and it is real evidence. It just is not a measurement of water. 2 other instruments push the case further. The Moon Mineralogy Mapper, usually shortened to M3, flew on India's Chandrayaan-1 mission and mapped the surface in infrared, looking for the specific spectral fingerprints that water ice leaves in reflected light, and the Lyman Alpha Mapping Project, LAMP, aboard the Lunar Reconnaissance Orbiter, looked in the far ultraviolet. Both detected signatures consistent with water ice exposed at the surface inside permanently shadowed regions, and both arrived at the same disappointing qualifier, which almost never survives the trip into popular coverage. The surface ice they detected is patchy, and it is of low abundance. Not a sheet, not a field, not a frozen lake under the dust. Patches, scattered, thin, at concentrations that in most places amount to a small percentage of the surface material at best. If the mental image you have been carrying is of astronauts chipping blocks of ice out of a crater wall, the orbital data does not support it and never has. More recently, an instrument called ShadowCam has been attacking the problem from a completely different angle, and the technique is remarkable enough to be worth a moment. If you want to photograph the inside of a permanently shadowed crater, you have no direct sunlight to work with, but the crater is not in absolute darkness. A small amount of light does reach the floor, sunlight scattering off the illuminated far wall, light bouncing off nearby terrain, and at the faintest level, starlight. It is an almost unimaginably dim environment, so you build a camera hundreds of times more sensitive than a conventional orbital imager, point it into the dark and take extremely long exposures. Work published in the scientific literature has used exactly this approach to search permanently shaded regions for surface water ice. And the technique works, in the sense that it produces images where none existed before. What it still cannot do is tell you what is under the surface, or how much of what you're seeing is ice rather than an unusually bright patch of rock, or an artifact of the extreme processing required to pull an image out of that little light. So let us total it up, because I think the honest summary is more interesting than either the optimistic or the dismissive version. We have multiple independent lines of evidence from different instruments on different spacecraft over more than 2 decades, all pointing the same direction. Hydrogen is concentrated at the lunar poles. Water ice exists inside permanently shadowed regions. The consensus on those 2 statements is solid, and anyone telling you the moon is bone dry is arguing against a large and consistent body of data. And we have no measured figure, none from anywhere, for how much water is present at any specific location, at what depth it sits, what physical form it takes, what it is mixed with, or whether any machine humans are capable of building could actually get it out of the ground. Everything in that second list is the part that decides whether people can live there, and every item on it is currently an assumption. I said earlier that the physical form is the thing that matters most, and it is worth being concrete about why, because this is where the abstraction becomes an engineering problem with a budget attached. Imagine 4 crater floors, each containing exactly the same total mass of water. On the first, the water exists as ice grains dispersed through loose regolith at a few percent by weight. To extract it, you scoop the soil and heat it, and the water comes off as vapor that you condense. That is a machine you could build with existing technology, and it would work. On the second crater floor, the same water is concentrated into a hard layer of ice-cemented regolith sitting under a meter of dry dust. That material has been compared to concrete. To get at it, you need to excavate the overburden, then cut through cemented material in a vacuum, at cryogenic temperatures, with equipment that cannot be lubricated conventionally, and cannot shed heat the way it would on Earth. That is not a scooping problem. That is a mining operation, and nobody has ever built mining equipment for that environment. On the third, the water is present as an extremely thin surface frost, a few molecules deep, spread across an enormous area. The total mass is the same. The energy required to sweep a large enough area to collect a useful quantity makes it functionally worthless. On the fourth, the hydrogen that the orbital instruments detected turns out to be mostly solar wind protons implanted in grain surfaces and hydroxyl bound in minerals, and the actual water ice fraction is a small part of the signal. In which case, the resource everyone has been planning around is substantially smaller than the map suggests. 4 scenarios, all consistent with the orbital data we currently have, all producing completely different answers to the question in the title of this video, and there is no way to distinguish between them from orbit. There never was. The only way to know is to go there, get inside the shadow, and take a sample. Which raises an obvious question, and it is the one that turns this from a science story into something considerably stranger. If the number is that important, and the ambiguity has been this well understood for this long, why has nobody done it? Part 3. Why water is the whole argument. There is a distinction that runs underneath every serious conversation about human spaceflight, and most public discussion never quite gets to it. The difference between visiting a place and living in a place is whether you can make what you need once you arrive. That is it. That is the whole thing. Apollo visited. 12 people walked on the moon between 1969 and 1972, and every single molecule they consumed, every breath of oxygen, every sip of water, every gram of fuel that lifted them off the surface again, was carried there from Earth. That is why the longest Apollo surface stay was about 3 days. Not because the crews were fragile, and not because the technology failed, because they were living entirely out of what they had brought, and what they had brought was measured against the brutal arithmetic of what a Saturn V could lift. Everything about the current pushback to the moon is an attempt to break that arithmetic, and the tool for breaking it is water. Let me build the case one use at a time, because each one is significant and together they are transformative. Start with the simplest. People drink water. A crew member on the International Space Station goes through several kilograms of water a day when you count drinking, food preparation and hygiene, and that station recycles aggressively. A very large fraction of what goes in comes back around through the water recovery system. Even with that recycling, water is one of the heaviest consumables in the logistics chain. Now take that requirement to the lunar surface, where there is no regular resupply flight, and stretch the mission from days to months. The mass adds up fast, and every kilogram of it has to be launched from Earth, thrown across 384,000 kilometers, and landed softly on another world. Second use. People breathe, and water is a way to make them breathe. Run an electric current through water, and it separates into hydrogen and oxygen. The chemistry is elementary, it is a school experiment, and the hardware is well understood because it is exactly how the oxygen supply on the space station works. The cost is power, and power on the sunlit polar rims is the one thing the lunar South Pole has in abundance. So a base with access to water and access to sunlight has, in principle, an air supply that does not need to be shipped. Now the third use, and this is where the strategic picture changes shape entirely. Water is rocket fuel. Split it, and you get hydrogen and oxygen. Chill them down and you have liquid hydrogen and liquid oxygen, the highest performing chemical propellant combination in common use, the pairing that flew the upper stages of the Saturn V and the main engines of the space shuttle. The two components of the most efficient rocket propellant humanity has are also the two components of water. Consider what that means for the economics of leaving Earth. Right now, everything about spaceflight is dominated by the tyranny of the gravity well. To reach low Earth orbit, you need to accelerate to roughly 7.8 kilometers per second, and because the fuel you burn at the end of the flight has to be carried and accelerated from the beginning of the flight, the mass penalty compounds savagely. The rule of thumb across the industry is that only a few % of the mass sitting on the launch pad ends up as useful payload in orbit. Push onto the moon and land there, and that fraction becomes brutal. Now consider the moon's own gravity well. Lunar escape velocity is about 2.4 kilometers per second. Getting off the moon is not a little easier than getting off Earth. It is easier by a margin that transforms what is possible. A ton of propellant manufactured on the lunar surface and lifted into lunar orbit costs a small fraction of the energy that the same ton would cost if launched from Cape Canaveral. So a vehicle that can refuel at its destination is not an incrementally better vehicle. It is a different category of machine. It does not have to carry its return trip with it. And once you can refuel in space, the whole architecture of exploration past the moon changes, because you are no longer paying Earth's gravity tax on every gram of everything, forever. That is the prize. That is why the money is moving. Not the flags, not the footprints, not the science alone. The possibility that the moon contains, in its permanently shadowed craters, a fuel depot that has been quietly filling itself for billions of years. And this is exactly where the central thread of this video tightens, so let me put it directly. Every architecture I have just described, the drinking water, the oxygen, the propellant, the entire concept of a base that sustains itself, is contingent on a quantity that has never been measured. Not measured badly, not measured with large error bars, never measured at all, on the ground, in the place where it's supposed to be. Now, why the poles specifically? I touched on this earlier, but it deserves a proper answer, because people reasonably ask why we cannot simply set up somewhere more convenient. The moon does have hydrogen and oxygen elsewhere. The regolith across the entire lunar surface is roughly 40% oxygen by mass, locked chemically into minerals, silicates, oxides, ilmenite. You can get that oxygen out. There are several demonstrated processes for doing it, and NASA has flown technology demonstrations aimed at exactly this. But every one of those processes is energy hungry, because you are breaking strong chemical bonds to prise oxygen out of rock, and none of them gives you hydrogen, because outside the cold traps there essentially is not any. The solar wind delivers a trickle of protons to the surface, and sunlight drives most of it straight back off again. At the poles, in the shadows, you get both halves in one place, pre-assembled in the form of a molecule that took no energy to make. That is the difference. It is not that the poles are the only place with useful material, it is that the poles are the only place where the material is already in the form you want it, which produces one of the more remarkable convergences in the history of exploration. Every serious lunar architecture on Earth, the American program, the Chinese program, the European contributions, the commercial ventures selling delivery services and future mining rights, routes through the same handful of square kilometers at the lunar South Pole. Not because anyone coordinated it, because the physics leaves no alternative. There are only so many places with sustained sunlight next to permanent shadow, and everyone with a slide deck has independently arrived at the same short list, and the entire convergence rests on inference. I want to draw out one asymmetry here that I think is underappreciated, because it changes how you should read every announcement in this field over the next few years. A low number would be more disruptive than a high one. If a machine gets into a permanently shadowed crater and reports that the water content is far higher than expected, in a form that is easy to extract, that is a wonderful result, and it accelerates everything that is already planned. Nobody has to redesign anything. The plans simply get better. But if the same machine reports that the water is scarcer than assumed, or bound up in a form that resists extraction, or concentrated into cemented layers that need heavy machinery nobody has funded, then a very large amount of planning built on the optimistic assumption has to be revisited. Base architectures, propellant depot business cases, landing site selection, the rationale for the pole itself. Almost all planning quietly assumes the good outcome. That is not a conspiracy, it is just how institutions work. You plan against your best estimate and you refine as data arrives. But it does mean the system is structurally exposed to a disappointing result in a way it is not exposed to an encouraging one. And a single credible in situ measurement would immediately constrain all of it. It would tell you how much equipment mass a base needs to allocate to extraction. It would tell you whether propellant production is a realistic near-term goal or a distant one. It would tell you whether the specific crater you sampled is a target or a waste of a landing. And most valuably of all, it would calibrate every remote sensing dataset ever collected. Because the moment you have one ground truth point, every orbital map that covers that point can be checked against reality and corrected everywhere else. One number, enormous leverage, and it is missing. It is worth pausing on the power side of this, because water extraction is often discussed as though the only hard part is finding the ice, and the energy budget is where most of these plans actually get uncomfortable. Splitting water into hydrogen and oxygen takes a substantial amount of electricity. That is not a criticism of the process, it is thermodynamics. You are storing energy in the chemical bonds you create, and you cannot get out more than you put in. Liquefying the products afterward takes more energy again, because hydrogen has to be chilled to within a few degrees of absolute zero to become a liquid, and keeping it there against any heat leak at all is a continuous cost. Then add the extraction itself. If the water is bound in cold regolith, you have to heat that regolith to drive the water off, and you have to do it in an environment among the coldest ever measured, where every joule you add is fighting a thermal gradient that wants to pull it straight back out. So a propellant plant at the lunar South Pole is, before anything else, a power station. And the power has to come from solar arrays on the illuminated rims, which means the whole architecture depends on that second piece of polar geography just as much as the first. Light on the high ground is not a convenience that helps the mission survive, it is the fuel supply for the fuel supply, which is why the concentration number matters so acutely. Every percentage point of water content you lose is a proportional increase in how much regolith you have to move and heat for the same output. A resource at 5% by weight and a resource at 0.5% are not the same resource with different numbers attached. One is a plant, the other is a quarry with a plant on the end of it. So who was going to go and get it? 3 machines were built to close this gap, and their stories are the rest of this video. One of them is a small thruster-powered probe that is designed to fly off a lit crater rim, cross into permanent darkness, and take a sample where nothing has ever operated. It is bolted to the top of a rocket right now on a tropical island in the South China Sea, and it is scheduled to launch in a matter of days. The second is a rover carrying a drill, built specifically to spend 100 days at the lunar South Pole prospecting for exactly this. It is finished. It cost around $450 million. It is sitting in a building in the United States, and as of this recording it has no confirmed ride to anywhere. The third was not a prospector at all. It was a station meant to orbit the moon and serve as the waypoint that made everything else possible. and a review board looked at its main habitable module and assessed the probability of it making its launch date at 0%. We have committed to a destination on the basis of a resource nobody has confirmed is usable. So the question that carries the rest of this video is not really whether there is water on the moon. It is why the country that has committed the most money to needing that answer is the one that stopped trying to find it. Part 4. 18 Instruments and a Thing That Jumps. On an island in the South China Sea, at a launch complex built into the tropical coastline of Hainan, there is a rocket being prepared for a mission whose entire purpose is to take one measurement. The site is Wenchang. The rocket is a Long March 5, China's heavy lifter, the vehicle they use when a payload is too large or too demanding for anything else in the fleet. And the payload sitting on top of it is called Chang'e 7. The spacecraft has already arrived at the launch site. The public target is August of 2026, and the schedules that track these things list the 24th of August, with a status that reads, "In the dry language of launch manifests to be confirmed." I want to flag that clearly rather than paper over it, because you are going to see a lot of coverage in the coming weeks stating the date as though it were fixed. It is not fixed. It is targeted. Launch campaigns slip, and this one may. But the hardware is there, and what that hardware is designed to do is the reason this video exists. Chang'e 7 is the cornerstone mission of the fourth phase of the Chinese lunar exploration program, with implementation beginning in 2022. And the architecture is unusual enough that it is worth taking apart piece by piece, because most coverage compresses it into a Chinese moon mission and loses everything that makes it interesting. There are 4 separate spacecraft launched together as a single stack. The first is an orbiter, which will remain in lunar orbit conducting remote sensing and relaying communications. The second is a lander, which will descend to the surface and serve as the fixed base of operations. The third is a rover, which will roll off the lander and traverse the surrounding terrain. And the fourth, the one everything in this story turns on, is a small thruster-powered flying probe. Chinese mission literature describes it as a mini-flying probe, and in English coverage it is usually just called the hopper. It does not drive, it flies. Between those 4 vehicles, Chang'e 7 carries 18 scientific instruments. Now, before I explain why the hopper matters, let me deal with the orbiter, because it is doing more work than the headlines suggest. The orbiter carries 5 principal payloads. The first is a high-resolution stereo mapping camera, which images the surface from 2 angles simultaneously, so that the terrain can be reconstructed in 3 dimensions. That gives you topography, the shape of the ground, the depth of craters, the height of rims, and therefore the illumination conditions at any point across the lunar year. The second is a miniature synthetic aperture radar. Radar penetrates. Where a camera stops at the surface, radar can probe the structure underneath it, and radar echoes are sensitive to the presence of ice in ways that visible light is not. The third is a wide-band infrared spectrum mineral imaging analyzer, which reads the composition of the surface across a broad range of infrared wavelengths, identifying minerals and looking for the spectral fingerprints of water-bearing compounds. The fourth is a neutron and gamma-ray spectrometer. This is the same family of instrument I described in the last part, the one that counts neutrons leaking out of the regolith to infer hydrogen concentration. Chang'e 7 is bringing its own. And the fifth is a magnetometer, measuring the local magnetic environment, which sounds peripheral until you remember that the moon has patches of crustal magnetism that affect how the solar wind interacts with the surface, which in turn affects where volatiles can accumulate and survive. Taken together, those 5 instruments give you the regional context, and regional context is not a nice-to-have here. It is essential because of a limitation I am going to keep returning to. A single ground measurement taken at a single point is meaningless unless you can place it inside a map. If the hopper lands in one spot inside one crater and reports a number, the only way to know whether that number means anything about the rest of the pole is to have mapped the rest of the pole with instruments you can now calibrate against it. The orbiter builds the map, the hopper provides the anchor, that is the design. So, the hopper. This is the part of the mission that has never been done, and I want to describe what it is actually for before describing how it works, because the what is genuinely remarkable. It is designed to leave the sunlit rim of a crater under its own thrust, fly across the boundary into a permanently shadowed region, descend to the surface inside that permanent darkness, and take measurements in place. Nothing has ever done that, not once, by anybody, at any pole, on any world. The instrument it carries for that job is designated Lunar. the Lunar Soil Water Molecule Analyzer, and the name tells you exactly what the mission is for. Not water in general, not volatiles in the abstract. Water molecules in lunar soil measured directly, in the terrain where the entire argument about human presence on the moon has been located for the past 2 decades. If that hopper reaches a permanently shadowed region and Lunar returns data, it will be the first direct ground-level measurement of water inside a lunar permanently shadowed crater in the history of the species. Now let me be exact about something, because it matters, and it is where a lot of commentary about this mission goes wrong. Chang'e 7 carries no people. There is no crew, it does not land astronauts, it does not beat anyone to anything human, and it has nothing to do with the flag-planting competition that dominates coverage of lunar exploration. It is a robotic prospecting mission. Its significance is informational. I say that plainly because the accurate version of this story is already strong enough that inflating it would be both dishonest and unnecessary. The reason this mission matters is not that it is a landing, it is that it is a measurement, the specific measurement that everything else has been waiting on. The program's own stated aim is scientific and resource exploration of the lunar South Pole, with particular emphasis on mapping resources and seeking water ice and other volatiles in permanently shadowed regions. That is the mission in the mission's own words, and here is a detail that I find genuinely clarifying, given how often this program is discussed as though it were opaque. The scientific objectives and the full payload configuration of Chang'e 7 were published openly in a peer-reviewed journal years before launch. Anyone can read what the instruments are and what they are meant to measure. This is not a black box. It is a published research program with a launch date attached. It also arrives on top of a program that has been building toward this for close to 2 decades, and the sequence matters because it explains why the hopper is being attempted now rather than as a first step. The Chang'e missions have worked upward in difficulty in a deliberate order: orbit first, then landing, then roving, then, in January of 2019, a landing on the far side of the moon, a place no spacecraft had ever touched down, and which carries a problem that turns out to be directly relevant here. The far side never faces Earth, so a lander sitting on it has no line of sight to any ground station on this planet. Radio does not bend around a world. To operate there at all, China first had to place a relay satellite in a position where it could see both the far side and the Earth simultaneously, and route every command and every byte of data through it. That same problem reappears at the South Pole in a slightly different form. A spacecraft sitting low on polar terrain, surrounded by crater rims and ridges, does not have a clean view of Earth either. The Earth hangs near the horizon from there, and terrain blocks it, which is part of why Chang'e 7 flies with its own orbiter rather than relying entirely on ground stations. The orbiter is doing double duty as a science platform and as a communications link, passing overhead on a schedule and carrying data down. And it is why the mission after this one already exists in the plan. The program's stated architecture continues past Chang'e 7 toward resource utilization demonstrations at the same pole. This is not a one-off flight. It is a step in a sequence that was laid out years in advance, published, and then executed roughly on schedule, which is a sentence that will land differently once we get to what happened on the American side. The rover deserves a word too, because it is easy to overlook when the hopper is the headline. A rover on the illuminated terrain is doing the unglamorous work that makes the exciting result usable. It extends the sampling footprint away from the single spot where the lander happened to touch down. It carries the surface measurements out across varied ground, so that when the hopper returns its number from inside the shadow, there is a local context to place it in, rather than one isolated data point floating in the dark. 4 vehicles, 18 instruments, 1 question. So why a hopper? Why not a rover, which is the obvious answer and the one everyone else reached for? Walk through the problem as an engineer would, and the design becomes almost inevitable. You want to operate inside a permanently shadowed region. The first thing you lose is solar power, and you lose all of it. Permanently. There is no sunlight. There will never be sunlight, so whatever goes in is running on stored energy or on a nuclear source, and nuclear sources are heavy, expensive, and politically complicated to launch. The second thing you lose is thermal control the easy way. Spacecraft on the sunlit moon spend a lot of their engineering budget getting rid of heat. Inside a cold trap, the problem inverts violently. You're sitting on a surface among the coldest ever measured, and everything about the machine wants to freeze, Batteries lose capacity in the cold, lubricants stiffen, mechanisms bind, electronics that work perfectly at room temperature start behaving strangely, then stop. The third thing, and this is the one that kills the rover concept, is that a wheeled vehicle has to drive back out. Think about what that means. Your rover crosses the boundary into shadow with a fixed energy budget and a clock running down as the cold eats into its systems. Every meter it drives inward is a meter it has to drive back. Every minute it spends measuring is a minute of battery it will not have for the return. The terrain inside these craters is rough and unmapped because we cannot image it properly, and if the vehicle gets stuck or picks a bad route or simply spends slightly too long taking data, it does not come back out and the mission ends there in the dark. Now invert the problem with a flying vehicle. The hopper sits on the sunlit rim, connected to the mission's power infrastructure, warm, charged, in the light. When it is ready, it lifts off on thrusters, flies a short ballistic arc across the boundary, and comes down inside the shadow. It does not have to negotiate the terrain, because it goes over it. It does not have to worry about getting stuck because it never touches anything on the way. It takes its measurements on a tight schedule, on stored power, in a window it can plan against. And then it lifts off again and returns to the light to recover. The trade being made is duration for access. A hopper cannot survey a crater for 100 days. It cannot drive a transect across varied terrain, building up a profile. What it can do is get somewhere that nothing else can reach, and do it more than once. That is the bet. Short visits to a place that has never been visited, rather than a long stay somewhere merely difficult. And every part of that design, the light on the rim, the dark on the floor, the short flight between them, depends entirely on where the mission puts itself down. Part 5. The Rim of Shackleton. There is a crater at the bottom of the moon named after a man who never reached the pole he set out for. Ernest Shackleton turned back roughly 180 kilometers short of the South Pole in 1909 because he calculated that continuing would kill his men, and he chose the retreat over the record. The crater carrying his name sits almost exactly at the lunar South Pole, and it has become the single most studied piece of terrain off this planet. The lander, rover, and hopping probe of Chang'e 7 are expected to touch down on the illuminated rim of that crater. I want to be careful with that sentence, because precision matters here. As of the most recent public reporting, no final landing area had been formally announced. The Shackleton Rim is the known preferred candidate. It has been the preferred candidate for a while, for reasons that will become obvious in a moment, and the mission has been described in those terms repeatedly. But if you hear a specific coordinate quoted with confidence in the coming weeks, treat it with some caution. So why the rim and not the floor? Because the floor is the science target, and the rim is the only place a solar-powered spacecraft can survive. This is the adjacency I described in the first part of this video, and standing at Shackleton is where it becomes concrete rather than theoretical. The crater is roughly 21 kilometers across and about 4 kilometers deep. Its rim stands high above the surrounding terrain, and because the sun at the lunar South Pole circles low around the horizon rather than climbing overhead, that elevated rim catches sunlight for an extraordinary fraction of the lunar year. Certain points along it, and on the ridges connecting Shackleton to neighbouring craters, are among the best illuminated locations on the entire moon. 4 kilometers below, on the floor, the sun has never risen. Not once. Not in the entire history of the crater. The vertical distance between the best lit real estate on the moon and terrain that has never been lit is, at Shackleton, about the height of a large mountain. The horizontal distance in places is a few kilometers. You could see the boundary from the rim. You could, in a suit and with a great deal of care, walk down toward it. That geometry is the entire reason this crater dominates the planning documents of every space agency that has any lunar ambitions at all. Now think about what that means for the mission design, because it explains the whole architecture. The lander sets down in the light, where its solar panels work and its systems stay warm through the long lunar cycle. The rover works the illuminated terrain around it, extending the reach of a fixed platform, mapping and sampling in conditions where equipment can survive indefinitely. And the hopper is the only element that crosses the line. The entire mission is built around a boundary between sunlight and permanent shadow that in physical terms you could step over. On one side, a spacecraft can live for years. On the other side, nothing has ever operated at all. The thermal difference across that line is severe. Sunlit lunar surface at the poles does not get anywhere near as hot as the equator, because the sun is always low and its energy is spread across a shallow angle. But it is survivable, manageable, and well within the range that spacecraft engineers have been designing for since the 1960s. The interior of a permanently shadowed crater is a different regime entirely, among the coldest surfaces ever recorded anywhere, colder than the surface of Pluto. Materials behave differently down there. Assumptions that hold everywhere else stop holding. And here is the thing that makes site selection so strange at the lunar poles, and it is a point I want to make carefully because it sounds like a conspiracy, and it is the opposite of one. Every major program is aiming at the same neighborhood. The candidate landing regions published by different agencies for different missions cluster into a startlingly small area. Not because anyone is coordinating, and not because anyone is copying. Because there are only so many places on the moon where sustained sunlight sits directly against permanent shadow, and physics narrowed the list for everybody at once. When several independent teams with different budgets, different politics and different engineering cultures all arrive at the same shortlist, that is usually a sign the constraint is real rather than the choice being arbitrary. Which brings up the obvious question, and it is one people ask constantly. If this terrain is so important, why can we not just characterize it properly from here? We covered a version of this problem in the video from August 5th, when we went through the claims about objects supposedly recorded moving across the lunar surface, and had to work out what a modest telescope on Earth can actually resolve at that distance. The answer then, and the answer now, is humbling. From Earth, even with excellent equipment, the smallest features you can distinguish on the lunar surface are measured in hundreds of meters to kilometers, and that is for terrain in full sunlight. For the interior of a crater at the pole viewed at a grazing angle in permanent darkness from 400,000 kilometers away, the situation is not marginal. It is impossible, so you go to orbit. And in orbit you hit the same wall in a different form. The fundamental obstacle is that conventional imaging requires light, and inside a permanently shadowed region there is no light to image with. You cannot photograph what is not illuminated. Every one of the workarounds I described earlier, radar, neutron counting, ultraviolet, the extraordinary starlight photography of ShadowCam class instruments, exists because the direct approach is physically unavailable, and each of those workarounds gives you something real and stops short of what you need. Radar tells you about structure and roughness, and radar returns that look like ice can also be produced by blocky rubble. Neutron counting tells you about hydrogen over a footprint of tens of kilometers. Starlight imaging tells you what the surface looks like in a photograph so dim that separating a bright ice patch from a bright rock is genuinely difficult. None of them tells you the concentration, in the soil, at a point. The uncomfortable fact sitting underneath all of the site selection, then, is this. Every serious lunar program on Earth has picked the same neighborhood on the basis of remote sensing, and nobody has ground truth for what is actually in it. There is one more complication worth naming, because it is going to matter enormously when we get to the landing attempt. Polar terrain is difficult to land on. The reasons compound. The ground itself is rough. The polar highlands are ancient, heavily cratered and steeply sloped in places. The lighting that makes the rim survivable also makes it visually treacherous, because a sun that never rises high produces shadows that are extremely long and extremely dark, with almost no scattered light to soften them. A landing camera looking at that terrain sees regions of blinding brightness, immediately adjacent to regions of total black, with very little in between, and terrain hazards can hide entirely inside those shadows. Landing at a lunar pole is not the same problem as landing on a mare. Several missions have found that out. Consider what a landing camera is actually doing during a descent. It looks at the ground, identifies features, compares what it sees against a stored map, and works out where it is and where it is going. A technique called terrain relative navigation, and it is now standard on precision landers. It works beautifully when the surface is evenly lit, because the features it needs are visible and consistent. At a lunar pole, the surface is not evenly lit. A boulder that would cast a short shadow at the equator casts one stretching many times its own length, and inside that shadow the camera sees nothing at all. The map the vehicle is comparing against was itself built from images taken in similarly awkward lighting, at a different point in the lunar cycle, with shadows falling in different directions. Then there is the slope problem. The polar highlands are ancient terrain, worked over by billions of years of impacts, and the ground around Shackleton is not a plain. A lander touching down on a slope beyond a few degrees risks tipping, and a tipped lander at the lunar South Pole is a mission that ends in the first minute. Every metre of slope tolerance has to be bought with landing gear mass, which comes directly out of payload, and underneath all of it is the fuel margin. A landing is a controlled fall with a finite propellant budget, and every second spent hovering while the guidance system resolves an ambiguity is propellant that cannot be spent on the touchdown itself. Missions have run out at the last moment. The polar lighting conditions make ambiguities more likely, which makes hovering more likely, which eats the margin. None of this is an argument that the landing will fail. Landers succeed at difficult sites regularly now. It is an argument that the first genuinely hard part of this mission happens long before anything crosses into the shadow, and that if you are following the coverage over the coming months, the touchdown is the moment to watch, rather than the launch. So Chang'e 7 has to arrive at a site chosen from orbit, in lighting that fights the sensors, on terrain that punishes error, and then it has to do the thing nobody has done. Send a machine off the edge of the light and into the dark. What happens next is the part that has never happened. Before we go over the edge, one more thing about this terrain that I think is underappreciated, because it changes the shape of what a base would actually look like. The illuminated ground at the lunar South Pole is not one continuous sunlit plain. It is a set of high points, crater rims, ridges, isolated peaks, separated by lower terrain that spends far more time in shadow. And critically, the specific spots that are best illuminated are not all illuminated at the same time. As the sun circles the horizon through the lunar month, the shadow pattern rotates with it, so a location that is lit now goes dark in a week, while a ridge 4 kilometers away comes into the light. That produces a genuinely unusual design constraint. A permanently powered outpost at the pole does not necessarily want to sit on the single best lit point. It may want to be distributed, several arrays on several high points, connected by cable, so that whichever one is currently in sunlight is feeding the whole system. Or it may want to be mobile, chasing the light around the terrain as the shadows swing. Some of the most cited illumination studies of this region are essentially maps of that problem. For every point at the pole, what fraction of the lunar year is it lit, and how long is its longest continuous darkness? That second number is the one that kills you. A location lit 90% of the time is useless if the missing 10% arrives as a single, unbroken week of cold, because you have to carry enough stored power to survive it. So the real estate everybody is competing over is not simply high ground near shadow. It is high ground near shadow with a short worst-case night. There are very few such places, and Shackleton's rim and the ridges leading away from it contain a disproportionate share of them. Part 6. Into the Dark. Picture the sequence, because it is worth holding in your head. The hopper sits on the illuminated rim, charged, thermally stable, in sunlight that has been falling on that ridge almost continuously for as long as the terrain has existed. Below it and ahead of it, the ground falls away toward a boundary that is not gradual. The transition from full sun to permanent shadow at the lunar poles is abrupt, because there is no atmosphere to scatter light and soften the edge. It is a line. The thrusters fire. The probe lifts, arcs, crosses the line, and everything changes at once. The sunlight stops. The temperature drops toward numbers that do not have useful everyday comparisons, and it descends, on stored power, toward a surface where nothing built by human beings has ever operated. Then it takes a sample, and Lunar goes to work. I want to spend some time on what that measurement actually means, because the contrast with everything in the second part of this video is the whole point, and it is easy to lose in the excitement. The L-cross result was a plume observed from a distance for 4 minutes by a spacecraft that was itself about to crash. The neutron results are hydrogen concentrations inferred from particle counts averaged over tens of kilometers in an unknown chemical form in the top meter. The infrared and ultraviolet results are spectral signatures of surface frost, patchy and of low abundance, red-off reflected light. The starlight imaging is a photograph so faint that its interpretation is contested. Every one of those is a measurement of something adjacent to the question. An instrument sitting on the floor of a permanently shadowed crater with soil in front of it, reporting how many water molecules are in that soil. That is the question itself. That is the difference between inference and observation, and it is the difference this entire field has been waiting on for a generation. Now, the honest part. There are 3 separate things that have to go right, and the coverage is going to blur them together into a single success or failure story. They are not the same thing, and I would rather you have the accurate framework in advance. The first is reaching the crater. The hopper has to survive the launch, the cruise, the lunar orbit insertion, the landing of the whole stack on a difficult polar rim, deployment, and then its own powered flight across the boundary, and a controlled descent inside a region nobody has ever imaged properly. Any one of those steps can end the mission. The second is surviving long enough to operate. Getting into the shadow is not the achievement. Getting into the shadow with functioning instruments, adequate power, and a machine that has not seized up in the cold is the achievement, and it has to happen fast because the thermal clock starts running the moment it crosses the line. The third is returning a number that is actually accurate. This is the one nobody will talk about, and it is the one that matters most. An instrument operating at the edge of its thermal envelope, in an environment it was tested for but never flown in, sampling material whose properties are unknown, can absolutely return a measurement that is precise and wrong. Calibration in those conditions is genuinely hard. Entering is not measuring. Measuring is not measuring well. Keep those separate as the news comes in. Assume, though, that it works. What does the number settle? It settles concentration by weight at the sample point, the single most requested figure in lunar resource planning. It settles physical form, at least locally, whether the water is dispersed through the regolith, bound into a cemented layer, or sitting as a surface frost. And depending on how the sampling works, it may say something about depth distribution, whether the concentration rises or falls as you go down, which is the difference between a resource you can scrape and a resource you have to excavate. Those 3 facts, from one location, would be the most valuable planetary science data returned in years. And now the limitation that almost nobody is going to mention, so let me mention it clearly. One sample is not a survey. A single measurement, at a single point, inside a single crater, tells you what is true at that point. It does not tell you whether that point is representative of the crater floor, let alone of the pole, let alone of the moon. Cold traps are heterogeneous. The distribution of volatiles inside them almost certainly varies with local topography, with the age of the surface, with impact gardening, with a dozen processes we understand poorly. Land in a rich patch and you overestimate. Land in a barren one and you write off a resource that is genuinely there 50 meters away. This is exactly the weakness that Viper, the rover we are going to come to shortly, was designed to avoid by driving 100 days across varied terrain and building a profile instead of a point. So why does a single point matter so much if it cannot be generalized? Because of calibration. This is the part that makes the mission genuinely transformative rather than merely historic, and it is worth being precise about. Right now we have decades of orbital data across the entire lunar polar region. Neutron maps, radar returns, infrared spectra, ultraviolet signatures. All of it is uncalibrated in the sense that matters. We know how the signals vary from place to place, but we do not know what any specific signal value corresponds to in actual water content, because we have never been able to check one against reality. Put one ground truth measurement at a known location, and every one of those datasets acquires an anchor. You can go to the orbital data for that exact spot, see what the instruments reported, compare it to what is actually in the ground, and derive a conversion. And once you have that conversion, you can apply it, carefully, with appropriate caveats, but genuinely, across every other place those instruments have looked. One point does not map the moon. One point calibrates the maps we already have. That is why the first in situ number is worth more than the second, the 10th, or the 100th. It converts an entire field from relative measurement to absolute measurement in a single stroke. Let me walk the 3 outcomes, because they are not equally likely and they are not equally interesting. The first outcome is the high number. Lunar reports substantial water content in a form that could be extracted with equipment we know how to build. Everything currently planned gets easier. Propellant production moves from aspiration to engineering. The business cases firm up. This is the scenario the industry expects, and it is the least disruptive. The second outcome is the low number. Lunar reports concentrations far below what the architectures assume, or finds that most of the hydrogen signal is not water at all. And this, as I said earlier, is the genuinely disruptive result, because an enormous amount of planning has quietly assumed otherwise. A base designed around local resource extraction that turns out to have very little local resource is a base that needs redesigning, or relocating, or reconsidering entirely. The third outcome is the most likely, and it is the one that will make for the most frustrating headlines. Something ambiguous, heterogeneous, water present but harder to get at than hoped, in a form that is neither the dream nor the disaster, with error bars wide enough that both optimists and pessimists can read the result as vindication. That is what first ground truth usually looks like. It is what it looked like when we first measured Martian soil and Venusian atmosphere and comet composition. The first direct number rarely settles an argument, it reframes it. There is also a question that has nothing to do with physics and everything to do with how science actually moves, which is what gets released and when. A measurement taken inside a permanently shadowed crater is a scientific result, and scientific results from any national program go through internal review before they go anywhere else. Raw instrument data is rarely published immediately by anybody. Not by China, not by NASA, not by the European agencies. Calibration takes time, analysis takes longer. The first public statement about what Lunar found may well be a summary figure in a press release long before anything appears that another team could independently check. That gap matters, because the value of a ground truth measurement depends entirely on the community's ability to use it. A number announced without the supporting data is a claim. A number published with its calibration, its uncertainties, and its methodology is a tool. Which of those two things arrives, and how long the second takes to follow the first is worth watching as closely as the result itself. The Chang'e program has a reasonable record on this, for what it is worth. Sample material from earlier missions has been made available to researchers, including researchers outside China, and the mission's own objectives and payload configuration were published openly in a peer-reviewed journal before launch. That is not nothing. But planetary science runs on independent verification, and the first in situ water measurement in history is exactly the kind of result that will attract intense scrutiny about exactly how it was obtained. But it reframes it around evidence instead of assumption, and that alone is a permanent change. There is one more consequence, and it is not scientific. It is strategic, and it follows regardless of what the number turns out to be. Whoever holds the first in situ dataset holds the calibration for everyone else's remote sensing. Every agency and company with lunar ambitions has orbital data. None of them can convert it into absolute water content without a ground truth anchor. The first organization to obtain one is, in a very real sense, holding the key that unlocks the value of everybody's existing archives, including archives collected by countries that are not going to be given the key. That is not a small advantage. It is not ownership of the moon, and I will come back to why that particular fear is misplaced. But it is a genuine, durable, informational head start on the question of where the useful ground is. And here is the part I keep circling back to because it is the strangest fact in this entire story. The country with the most to lose from that asymmetry built its own machine to prevent it. A rover with a drill designed to spend 100 days measuring exactly this at exactly that pole for exactly this reason. They finished building it, and then they stopped. Part 7. The Rover with a Drill. There was another machine built to answer this exact question, and it was American, and it was better suited to the job in almost every way that matters. Its name was Viper. The acronym stands for Volatiles Investigating Polar Exploration Rover, and the word doing the work in that name is volatiles, the light compounds, water chief among them, whose presence or absence at the lunar South Pole determines everything we have been talking about. Viper was a rover, roughly the size of a golf cart, and it carried a drill. That drill is the whole story. Because if you have been following the argument in this video, you already know the fundamental limitation of every measurement we have. Everything is surface or near surface, or inferred from a distance. The neutron instruments see the top meter and average over tens of kilometers. The infrared and ultraviolet instruments see a thin surface layer, and even the mission currently sitting on a launch pad in Hainan, the Hopper, with its water molecule analyzer, is going to land, sample where it lands, and take off again. Viper was designed to go down, Its drill was built to penetrate below the surface and bring material up in stages, so that the concentration could be measured as a function of depth, not one number, a profile, and it was designed to do that repeatedly over roughly 100 days while driving. I want to dwell on why the 100 days matters, because it is the single clearest advantage the American approach had, and it maps directly onto the limitation I raised in the last part. A hopper produces a point. A rover on a 100-day traverse produces a transect, a line of measurements across varied terrain, in and out of shadow, over different surface ages and different local topography. And a transect is what tells you whether a rich reading is a rich deposit or a lucky spot. It is the difference between knowing what is under 1 square metre and knowing how the resource is distributed across the ground you would actually have to work. If you were designing a survey to underwrite a multi-billion-dollar decision about whether human beings can live on the moon, you would want the transect. Obviously, you would want to know not just that water exists, but how it varies, where it concentrates, whether the concentration climbs with depth or falls, and whether the pattern is predictable enough to plan a mining operation around. That is what Viper was for. NASA's own framing of the mission was not abstract science. It was to map ice at the lunar South Pole that could in future be used by American astronauts. This was a supply survey, commissioned in advance of a program that would depend on the supply. The vehicle was designed around the specific difficulty we have been circling this whole video. Viper did not attempt to live inside a permanently shadowed region, because as I described earlier, that is a losing proposition for a solar-powered wheeled machine. Instead, it was built to work the illuminated margins, the sunlit ground around and between the cold traps, and to make limited excursions into shadow, going in on stored power, drilling, and getting back out to sunlight before the batteries and the thermal budget ran down. So the two approaches side by side are almost a perfect study in engineering trade-offs against the same unknown. The American answer was to spend a long time on the accessible edges of the problem, sampling repeatedly, building a depth profile and a spatial map, dipping into the dark and retreating. The Chinese answer is to spend a short time in the least accessible part of the problem, going where nothing has been, taking a number at the point that matters most and getting out. Duration against access, map against anchor. Both aimed at the same missing figure. Neither is obviously wrong. It is worth being concrete about what a depth profile actually buys you, because it sounds like a technical refinement and it is closer to being the whole answer. Everything we suspect about how ice accumulates in a cold trap implies that it should not be uniform with depth. The surface of any airless body is constantly worked over by micrometeorite impacts, a process usually described as gardening, which churns the top layer, mixes it, and exposes fresh material to the vacuum. Anything volatile sitting in that churned layer is periodically thrown up, exposed and partly lost. Go below the gardening depth and that stops. So the expectation, from theory, is that concentration should climb as you descend, at least until you reach whatever the local limit is. That expectation has never been tested, and it matters enormously, because it decides what kind of machine you send. If the water is concentrated in the top 10 centimetres, a scraper works. If it is negligible at the surface and rich half a metre down, a scraper returns almost nothing, and you have built the wrong equipment. If it climbs steadily with depth and keeps climbing past where any current drill reaches, then the resource may be far larger than anyone has estimated and also far harder to touch. One drill, taking material in stages, resolves all three of those possibilities in a single hole. That is why the survey was designed the way it was. There is also the delivery arrangement itself, which turns out to be part of why the mission died, and is worth understanding because it will shape the next decade of American lunar exploration regardless. Viper was not going to fly on a NASA-built lander. It was going to be delivered under a program in which the agency buys a ride from a commercial provider, the way you would buy freight. The logic is straightforward. Competition drives costs down, the agency stops paying to develop its own landers, and multiple companies build capability at once. The complication is that it splits a single mission across two organizations with separate schedules, separate budgets, and separate problems. The rover has its own cost growth, the lander has its own delays, and the total exposure of the mission is the sum of both, with neither party fully in control of the outcome. When both sides slip at once, as they did, the mission becomes expensive in a way that no single decision caused and no single decision can fix. except that only one of them is on a rocket. There is a detail about how Viper was meant to operate that I find genuinely elegant, and it makes the loss sharper. The rover was solar-powered, which at the lunar South Pole creates an immediate problem. The sun sits near the horizon, so a conventional horizontal solar panel on the top deck receives almost nothing. Light arriving at a grazing angle across a flat panel delivers a fraction of the power it would deliver head-on. So Viper's arrays were mounted vertically, on the sides of the vehicle facing outward, because at the pole, the sun is not overhead, it is beside you. That single design choice cascades into everything else. A rover with side-mounted panels has to think about its own orientation constantly, turning to keep its arrays facing a sun that moves around the horizon rather than across the sky. It has to think about its own shadow and about the shadows of the terrain around it, because a ridge that blocks the low sun blackens the panel completely rather than merely dimming it. Route planning becomes a power problem as much as a navigation problem. The vehicle is not simply driving from A to B, it is driving from light to light, with a hard limit on how long it can spend in between. That is the machine that was built to work this terrain, designed around the specific, awkward physics of a place where the sun never rises and never quite sets, engineered to survive on the margins and dip into the dark and come back. It exists. It is finished. On the 17th of July, 2024, NASA cancelled Viper. The figure attached to the cancellation was approximately $450 million already spent, and that figure does not include launch costs. Nearly $500 million gone into a program that would not fly. Now, I want to handle the reason fairly because there is a version of this that turns into a hunt for villains, and the truth is more mundane and more depressing than that. The stated reason was cost. Viper's budget had grown, its schedule had slipped, and NASA was making a portfolio decision inside a constrained envelope where continuing to fund an overrunning mission means cutting something else. That is a real institutional dilemma. It happens constantly across every space agency on Earth, and the people who made the call were not being frivolous. Agencies cancel programs. It is part of how they function. The specific mechanism was also more complicated than a simple budget line. Viper was going to be delivered to the lunar surface under a commercial contract, through the program where NASA buys delivery services from private landers rather than building its own. That arrangement is meant to be cheaper. It also means that the rover and its ride are on separate schedules, managed separately, slipping separately, with the mission's total cost exposed to problems on both sides at once. So, an overrunning payload, a delivery system with its own delays, a fixed budget, and a decision to stop. That is the honest version. It is not a cover-up. It is not sinister. It is a large organisation under financial pressure making a defensible call about a project that was costing more than it was supposed to. And it is also, when you set it against the argument of this video, an extraordinary thing to have done. Because the mission that was cancelled was the measurement, and the measurement is what everything built afterward depends on. The decision did not go unnoticed inside the American system either. Leaders of the House Science, Space and Technology Committee wrote to NASA seeking answers about the termination, which is a fairly clear signal that people with oversight responsibility for the agency found the reasoning insufficient at the time. Cancelling a mission on paper is one thing. Programs get killed at the design stage constantly, and nobody outside the field ever hears about it. This one was different, and the difference is the part that is genuinely hard to sit with. Part 8. Essentially complete. When NASA cancelled Viper, the rover was reported to be essentially complete. Sit with that for a second, because the phrasing is easy to skate over, and the physical reality is stark. This was not a concept that got expensive. It was not a set of drawings, or a subsystem in test, or a prototype waiting on a critical component. It was an assembled spacecraft. Built, integrated, carrying its drill and its instruments. Close enough to finished that the descriptions in the reporting at the time were about final testing rather than remaining construction. Roughly $450 million of engineering, and a machine designed to answer the most consequential open question in lunar exploration, standing in a building. Not going anywhere. NASA's stated fallback was that the agency might reuse Viper's scientific instruments and hardware on future missions, and I want to be precise about what that does and does not promise, because it reads as reassuring and it is not. Reusing instruments is not the same as flying the mission. an instrument distributed across other people's spacecraft, arriving at different places on different schedules, does not produce a 100-day depth-resolved transect of the lunar South Pole. It produces a scattering of individual readings. The thing that made Viper valuable was not the parts, it was the integrated survey. It is also worth understanding what essentially complete means in the specific language of spacecraft development, because the phrase is doing a lot of work. Building a spacecraft runs through recognized stages. You design it, you build and test the individual subsystems, you integrate them into a complete vehicle, and then you spend a very long time testing the integrated vehicle as a whole, shaking it on a vibration table to simulate launch, running it in a thermal vacuum chamber to simulate the environment it will operate in, exercising the software against every fault case anyone can imagine. That final testing campaign is expensive and slow, and it is where problems surface. A vehicle described as essentially complete has come through design, through subsystem build, through integration. The remaining work is verification rather than creation. In terms of cost, the overwhelming majority of the money is already spent, because the money goes into people designing, building and integrating, and those people have already done their work, which means the cancellation happened at close to the worst possible point on the curve, early enough that the mission produced no data, late enough that essentially all of the cost had been incurred. Kill a program at design review and you save most of the budget. Kill it after integration, and you have paid for nearly everything and received nothing. The other thing that happens to cancelled hardware is worth knowing, because it is rarely a clean story of preservation. A completed spacecraft is not a stable object. It contains batteries that degrade, propulsion components with limited shelf lives, seals that age, and software written against a specific launch date and a specific set of ground systems. Storing it costs money. Climate-controlled space, periodic testing, a small team retained to keep it alive. Every year it sits, the eventual cost of flying it goes up because more components fall out of certification and have to be replaced or requalified, and the team disperses. The engineers who built it, who know the undocumented quirks and the reasons behind the decisions that never made it into a drawing, move to other programs or other companies. That knowledge does not sit in a warehouse next to the hardware. It leaves. So a rover that is essentially complete today is not a rover that is essentially complete indefinitely. There is a window in which reviving the mission is a matter of finding a ride, and after that window it becomes a matter of partially rebuilding the vehicle with people who did not build it the first time. Nobody has stated publicly where the edge of that window is, but it exists and it is closing. Then there is the matter of the ride. Viper was contracted to be delivered to the lunar surface by a lander called Griffin, built by Astrobotic. Griffin was the vehicle. That was the arrangement. As of 2026, with Griffin rescheduled to fly in July of this year, it is carrying a different payload. The rover riding down on the lander that was built to deliver America's water prospector is Astrolab's Flex Lunar Innovation Platform, a mobility technology demonstrator. Read that sequence again in order. The prospector was cancelled. The lander it was going to ride survived. It flew, or is flying, with somebody else's rover on top. There have been serious attempts to rescue the mission, and they deserve mentioning because the story is not one of universal indifference. Multiple parties looked at a finished $500 million rover sitting idle and tried to find a way to get it off the ground. Intuitive Machines proposed flying Viper on a scaled-up version of its Nova C lander, potentially as soon as late 2026 or the middle of 2027. Where does that stand as of this recording? Unresolved. I am not going to imply a conclusion that has not been reached. The proposal exists. Whether it gets funded and flown is one of the genuinely open questions coming out of this whole story, and it is one of the things I will be watching. But here is where I want to bring this back to the central argument, because the sequencing is the part that I cannot get past. There is an obvious order to building anything that depends on a resource. You measure the resource, then you design around the measurement. That is not a sophisticated insight. It is how you would approach drilling a well, siting a factory, or planning a mine anywhere on Earth. You survey first. The survey is cheap relative to the thing it de-risks, and its entire purpose is to tell you whether the expensive thing makes sense before you commit to it. Now watch the American sequence laid out as a timeline. In July of 2024, the survey is cancelled. $450 million spent. Rover essentially complete. Mission terminated. In March of 2026, 20 months later, NASA announces a commitment of approximately $20 billion over 7 years to build a permanent base on the lunar surface. A base whose entire logic, whose whole reason for being at the pole rather than anywhere else, is the use of local resources. The survey is unfunded. The thing that depends on the survey is planned, budgeted and announced. And Chang'e 7, launching in a matter of days, restores the correct order: measure first, then build, for a different country. I want to be careful here, because there is a triumphalist version of this observation that I have no interest in, and that would also be inaccurate. This is not a story about Chinese brilliance and American incompetence. China's program has its own delays, its own cancelled elements, and its own gap between announcement and delivery, and its lunar program has been building toward this for 2 decades, with the advantage of a stable long-range plan rather than a budget that turns over with each administration. The observation is narrower than that, and I think more interesting. It is simply that the sequence got inverted, and that nobody appears to have treated the inversion as a problem worth solving. The counter-argument is worth stating at full strength, because it is a reasonable one. You could say that the measurement is not actually a prerequisite, that we know enough from orbital data to commit to the pole, that the base can be designed with margin to accommodate a range of outcomes, and that the ground truth can arrive during construction rather than before it. Engineering projects proceed under uncertainty constantly. Waiting for perfect information is its own kind of failure. That argument has force. It is, I suspect, close to what people inside the program would say if you ask them. But it only works if the range of possible outcomes is narrow enough to design against. And as I laid out earlier, it is not. The gap between water dispersed through loose regolith at a few % by weight, and water locked into a cemented layer under a metre of overburden, is not a margin you can carry. Those are different machines, different power budgets, different mission durations, different everything. You cannot design a base with enough margin to cover both. You have to know which one you're going to. The mining industry on Earth works this out early, and it works it out ruthlessly, and the comparison is instructive rather than rhetorical. Nobody builds a processing plant before drilling the deposit. The exploration phase, core samples, assays, a resource estimate with defined confidence categories, exists precisely because the capital cost of the plant is enormous and the plant has to be matched to the ore. Building a plant designed for one grade of ore and then discovering the deposit is a different grade is a well-documented way to destroy a company. So the sequence is enforced by the fact that the people financing it will not release the money without the survey. Space exploration has no equivalent discipline, because the financing does not work that way. The money comes from appropriations that are decided annually, on political timescales, by people balancing many competing objectives. A survey that produces a number in 4 years is worth less in that system than a program that produces an announcement now. The incentives point away from measuring first, and they point that way structurally rather than because anyone involved is acting in bad faith. That, I think, is the actual explanation. Not concealment, not incompetence, and not a grand strategic blunder. A funding system that rewards commitment over information, applied to a problem where information should have come first. And the mission that would have told us is in a building, essentially complete, waiting for a ride that may never come. Viper, though, was not the only thing cancelled. Part 9. 0%. A review board looked at a spacecraft module, assessed the probability that it would meet its launch date, and returned a figure of 0%. I have read a lot of program assessments over the years, and I want to convey how unusual that is. Review boards deal in probabilities and they hedge, because hedging is appropriate. Schedules are uncertain, problems get solved, resources can be added. Assessments come back as low confidence, or significant risk, or unlikely without substantial intervention. A board writing down 0 is a board saying there is no version of this that works. The module was called Halo, and to understand why that finding mattered, you need to know what it was part of. The Lunar Gateway was a small space station intended to orbit the Moon, not to land on it, to orbit it, in a particular kind of elongated path that swings close to the lunar surface at one end and far away at the other, chosen because it is stable, cheap to maintain, and reachable from Earth without an enormous fuel penalty. It had been in development for close to a decade. It was meant to be the first human outpost beyond low Earth orbit, the first place people would live that was not either on Earth or a few hundred kilometers above it. International partners had committed modules. It was, on paper, the centerpiece of the architecture, and the concept it embodied was a waypoint. Crews would launch from Earth, travel to lunar orbit, dock with the station, transfer to a separate lander, descend to the surface, come back up, dock again, and ride home. The station was the interchange, the place you stop on the way. Halo was the habitation and logistics outpost, the first pressurized module, the habitable core, the part with the air in it, the part where people would actually live. Without Halo, there is no station, because a station without a place to be is just a docking adapter with ambitions. So when the Standing Review Board assessed Halo's chance of meeting its launch readiness date at 0%, it was not commenting on a peripheral component. It was commenting on the piece that everything else attached to. The orbit itself is worth a moment because it explains a lot about why the waypoint concept was attractive in the first place, and why abandoning it is a real loss rather than simply a saving. A station in a low circular orbit around the Moon is a difficult thing to maintain. The Moon's gravitational field is lumpy. There are concentrations of dense material beneath the surface, left over from ancient impacts, and they tug on anything passing overhead. A spacecraft in low lunar orbit is therefore perturbed continuously, and needs regular propellant expenditure just to stay where it is, or it eventually intersects the ground. That is a genuine operational cost, forever. The orbit chosen for Gateway avoided that by being highly elongated, swinging in relatively close over one pole, and then far out on the other side. In that kind of path, the spacecraft spends most of its time well away from the lumpy field, station-keeping costs drop enormously, and communication with Earth is nearly continuous because it is rarely occulted by the Moon. It also has a useful property for polar operations specifically. The close approach can be arranged over the South Pole, which is exactly where everyone wants to go. So the waypoint was not an arbitrary piece of infrastructure. It was a solution to several real problems at once. A stable place to park, continuous communications, and repeated close passes over the terrain of interest. Whatever you think of the cost, the concept was not foolish. And then it said something worse. The board concluded that the program's lack of schedule realism may have been driving suboptimal engineering decisions during development. I want to take that sentence apart because it is written in the careful, bloodless register that these documents always use, and it is describing something genuinely serious. It is not saying the module was late. Late is normal. Every complex spacecraft in history has been late. It is saying that the schedule was so detached from what was achievable that the schedule itself was degrading the engineering. That people working on the hardware were making technical choices, real, physical, consequential choices about how to build a thing that human beings would eventually breathe inside, under pressure from a date that could not be met, and that those choices were worse than the ones they would have made otherwise. That is a failure mode considerably more alarming than a slip delivery. A late spacecraft is a schedule problem. A spacecraft whose design was distorted by an impossible schedule is a safety problem, wearing a schedule problem's clothes. It is worth understanding how a schedule does that to an engineering effort, because the mechanism is not mysterious, and it has appeared in the aftermath of more than one accident investigation. When a team is working toward a date it can meet, tests get run in the order that makes engineering sense. A problem surfaces, the team investigates it properly, understands the root cause, and fixes the cause rather than the symptom. Design reviews happen with time to respond to what they find. When the date cannot be met, and everybody knows the date cannot be met, but the date remains official, the behavior changes. Tests get deferred or run in parallel when they should have been sequential. Problems get closed with workarounds rather than root cause investigations, because the investigation would take 3 months the schedule does not have. Reviews surface concerns, and the concerns get logged as risks to be accepted rather than issues to be fixed. Nobody makes a single catastrophic decision. Everybody makes a series of small, individually defensible choices under time pressure, and the accumulated result is a vehicle that is less well understood than it looks on paper. That is what the board was describing. Not a specific flaw it had found, but a process that was producing flaws faster than it was catching them. And a finding like that raises an uncomfortable question about the hardware already built, because if the schedule was distorting decisions during development, some of those decisions are sitting inside modules that NASA now intends to repurpose for a surface base. The contract value, by the time a stop work order was issued to Northrop Grumman in April of 2026, had reached $1.9 billion. Here is the chronology, cleanly. On the 24th of March, 2026, at an event NASA branded Ignition, Administrator Jared Isaacman announced that the Lunar Gateway was being paused in its current form. Reporting at the time characterized the announcement, accurately enough, as the end of the program. In April, the stop work order went out. Now, the language question, because it is going to come up and I would rather address it than let it sit. NASA's own word is pause, not cancel. The official framing is that the program is paused in its current form and that much of the hardware will be repurposed. That is a meaningful distinction in principle. A paused program can restart, and repurposed hardware is not wasted hardware. Set it against the facts on the ground. A stop work order has gone to the prime contractor. Supplier contracts have been terminated, the workforce is being dispersed. Whatever the official verb is, the practical situation is that people have stopped building it and started doing other things, and that is a state programs very rarely come back from. I will let you weigh the distinction yourself. I would simply note that it is possible for an announcement to be technically accurate and still leave a listener with a substantially wrong impression of what has happened. There is a further consequence that received almost no attention at all, and it involves everyone else. Gateway was not a purely American project. International partners had committed hardware to it. Modules, robotics, resupply capability, under agreements negotiated over years. Those commitments represent budgets approved by other governments, industrial contracts signed in other countries, and engineering teams built up around a specific set of deliverables. When the centerpiece of an architecture is paused in its current form, every one of those partners has to work out what their contribution is now for. This is the quiet cost of a cancellation that does not show up in the domestic accounting. It is not measured in dollars. It is measured in the willingness of other space agencies to sign the next agreement, having watched what happened to the last one. Long-duration exploration depends on partners being able to plan a decade ahead, and a decade is considerably longer than the interval between changes of direction. The stated causes were repeated cost overruns and schedule delays, and this had been coming for a while. The fiscal year 2026 budget proposal had already explicitly cited escalating costs as grounds to end the program before the formal announcement arrived. So let me tie all of this back to the argument, because Gateway can look like a separate story and it is not. Gateway was a bet on the waypoint, the idea that the hard part of lunar operations is the transfer, and that what you need is somewhere to stage from. Viper was a bet on the survey, the idea that the hard part is not knowing what is in the ground. Within 20 months, both bets were called off. What remains is a destination, the lunar South Pole chosen because of a resource, and a commitment of $20 billion to build on it, without the waypoint that was going to make getting there routine, and without the survey that was going to establish whether the reason for going is real. A decision of that size does not stay invisible forever, but it took 5 months to surface, and when it did, it surfaced 2,000 miles from Washington, in a company most people have never heard of. Part 10, $20 billion and 70 people. On the 11th of August, 2026, a company in Tucson, Arizona announced a restructuring. Paragon Space Development Corporation is not a household name, and there is no reason it should be. It is one of the several hundred specialist firms that make American spaceflight physically possible without ever appearing in a photograph. Paragon builds life support, thermal control, atmosphere management, water processing, the systems that handle the unglamorous, absolutely non-negotiable business of keeping a human being alive inside a sealed volume in a place that would otherwise kill them in seconds. The announcement was a company-wide restructuring, and it laid off 70 people across Arizona, Colorado, and Texas. The reason was that Northrop Grumman had terminated Paragon's contract, and the contract was for the life support systems for Halo, so follow the line all the way down. In March, an administrator stands at an event and announces that a program is being paused in its current form. In April, a stop work order goes to a prime contractor. Some months later, that prime contractor terminates a subcontract, and in August, 70 people in 3 states are told their jobs are gone. The engineers who are building the equipment that would have kept the first human beings living beyond Earth orbit breathing. That is who absorbed the decision 5 months after it was made, 2,000 miles from where it was made. I want to spend a moment on that 5-month lag, because it is the mechanism that explains why almost nobody noticed any of this. Large programs do not stop the way a machine stops. They stop the way a ship stops. The decision at the top is instantaneous. The consequences propagate outward through a supply chain that is layered several deep: prime contractors, subcontractors, suppliers to the subcontractors. And each layer takes time to work through its contractual obligations, its existing purchase orders, its notice periods, and its own internal decisions about whether to absorb the loss or shed the workforce. By the time the decision reaches the bottom, the news cycle that covered the announcement has been over for months. The people writing about space policy in March are writing about something else in August, and the actual, human, measurable consequence of the decision arrives as a local business story in a regional paper. This is a general feature of how these things unfold, and it is worth carrying with you beyond this story. When a major program is cancelled, the moment of the announcement is the moment of least information. What it actually meant becomes visible much later, in layoffs and terminated contracts and hardware that quietly stops being built, at which point almost nobody is looking. It is also worth understanding what was actually being built in Tucson, because life support is one of those phrases that slides past without registering, and the reality of it is the most human part of this entire story. A closed-loop life support system has to do several things simultaneously and forever. It has to supply oxygen at the right partial pressure. Too little, and the crew loses consciousness. Too much, and everything becomes a fire hazard. It has to remove carbon dioxide continuously, because a human being exhales roughly 1 kilogram of it a day, and the concentration becomes dangerous long before the oxygen runs out. It has to control humidity, because people are wet and a sealed volume full of condensation grows things. It has to manage temperature against an external environment that swings by hundreds of degrees, and it has to process water, recovering it from humidity, from washing, from urine, and return it clean enough to drink over and over because there is no resupply. Every one of those functions has to work without failing, in microgravity or partial gravity, in radiation, for months at a time, with a crew that cannot walk outside if it stops. That is what those 70 people were working on. Not a component. The thing that decides whether a habitat is a home or a coffin. It is the single most safety-critical system on any crewed spacecraft, and the expertise to build it well lives in a small number of firms and a smaller number of individual engineers who have spent careers on the problem. When a program of this size stops, that expertise does not go into storage. It goes wherever it can find work, which may be another space company, and maybe a medical device firm or a defense contractor or somewhere else entirely. Rebuilding a team like that later is not a procurement exercise. It takes years, and some of the people do not come back. Now let me deal with the other half of that March announcement, because it was not only a cancellation, it was a redirection, and the redirection is genuinely substantial. NASA announced that it would repurpose much of the Gateway hardware and build a permanent base on the lunar surface instead. And the language used was specific. Approximately $20 billion over the next 7 years, built through dozens of missions, working together with commercial and international partners toward what was described as a deliberate and achievable plan. The build period discussed publicly runs from roughly 2029 to 2036. That is not a small announcement. $20 billion is real money even at agency scale, and a permanent surface base is a genuinely more ambitious objective than a small station in orbit. The strategic argument behind the pivot is also a reasonable one, and I want to give it at full strength rather than a weak version I can knock down. The argument goes like this. Gateway was a waypoint, and waypoints are only worth building if the traffic justifies them. If you are going to the surface anyway, and if landers can fly directly from Earth orbit to the surface and back, then the station is an expensive intermediate step that adds complexity, adds docking events, adds failure modes, and adds an entire additional vehicle that has to be built and maintained forever. Under that reading, Gateway was a solution to a problem that better landers make disappear. And the hardware already built for it does not have to be thrown away. Habitation modules, life support, power systems all have obvious applications on a surface base. That is a coherent position. Reasonable people hold it, and held it long before this decision was made. But here is where the whole video converges, and I want to state it as plainly as I know how. A surface base is a resource bet. That is the difference between the two concepts, and it is not a detail. A station in orbit does not need anything from the moon. It is supplied from Earth, and its logic is transport efficiency. A permanent base on the surface, at the South Pole specifically, sustained across dozens of missions over 7 years. That only makes sense if there is something in the ground worth being next to. If you were not planning to use lunar resources, you would not need to be at the pole. The pole is a hard place to land, a hard place to operate, and a hard place to communicate from. The equatorial regions are easier in every respect. The only reason to accept the difficulty of the pole is the volatiles. So the pivot did not reduce the dependence on the unmeasured number, it increased it. Gateway did not care what was in the craters. A surface base at Shackleton cares about nothing else. And the survey that would have told us is in a building in the United States, essentially complete, with no confirmed ride. There is a pattern we have come back to repeatedly on this channel, most recently in the video about the systems inside the Earth that turned out to be moving all along, that the rate at which we discover things tracks the capability of our instruments far more than it tracks any change in the world itself. We find things when we build something that can see them. This story is that lesson running in reverse. The discovery was not made because the instrument was cancelled. Now, the honest complication, and I do not want to let this slide past. These two decisions were made at different times, for different reasons, by different administrations through different processes. Viper was cancelled in 2024 over cost growth in a specific mission. Gateway was paused in 2026 as part of a strategic redirection with its own logic and its own review board findings. There is no evidence that anyone connected them, and there is no reason to think anyone intended the combined effect. Do not read coordination into coincidence. That is how perfectly ordinary institutional dysfunction gets mistaken for a plan, and it is a mistake this channel tries hard not to make. What is true, regardless of intent, is the state of affairs it produced. The waypoint is cancelled, the survey is cancelled, the destination is unchanged, and $20 billion is committed to building on ground whose defining property has never been measured. Meanwhile, the competition that everyone thinks they are watching has quietly moved somewhere else entirely. Part 11. The Race. Everyone is watching is the wrong one. Ask almost anyone what the moon race is about and you will get the same answer. Boots, flags, a date, and a nationality attached to it. That is the story that gets told, and there is a reason for it. A crewed landing is legible. It produces a photograph, a name, a moment you can point at. Robotic missions produce datasets, and datasets do not trend. So let me lay out where the crewed programs actually stand on both sides, as of this recording, and then explain why I think it is the wrong thing to be watching. Start with the American side. The landing has moved. It is no longer expected on Artemis 3. Reporting indicates the surface landing will now occur on Artemis 4, currently scheduled for 2028, with Artemis 3 reconfigured as something considerably more modest, an orbital rendezvous between a crewed Orion and a lander, without a descent to the surface. The comparison being drawn for that reconfigured mission is instructive, and it was drawn openly. Apollo 9, March of 1969. The mission where astronauts took the lunar module out for the first time and flew it in Earth orbit, docking and undocking, verifying it worked without going anywhere near the moon, a necessary step. Also, unmistakably, a step backwards from where the schedule used to say we would be. The reason is the lander, NASA's Aerospace Safety Advisory Panel, the independent body that exists specifically to tell the agency things it does not want to hear, has warned that the Starship human landing system could be years late for a mission in mid-2027, and that development has already slipped at least 2 years with further slippage expected. I want to attribute that clearly. That is the safety panel's assessment, not a settled fact, and the contractor would characterize its own progress differently. The internal targets that have been reported on the contractor side sketch out a sequence: an orbital propellant transfer demonstration between 2 vehicles, then an uncrewed landing on the moon, then the earliest crewed attempt at the surface somewhere around September of 2028. Propellant transfer in orbit is the pivotal item on that list, and it has never been demonstrated at the scale required. Everything downstream waits on it. NASA's response has been to open the lander contract to other providers, which is a fairly direct statement of confidence, and the spacesuits remain outstanding, with design work still needed on the life support, including larger oxygen tanks for surface operations. Now, the Chinese side. The stated goal is a crewed landing before 2030, and officials have described the effort in terms of sparing no effort to get there. 3 main pieces of hardware: the Long March 10 launch vehicle, the Mengzhou crew spacecraft, and the Lanyu lunar lander. The program describes development as proceeding. What has actually been demonstrated is more interesting than the rhetoric. A zero-altitude abort test of the crew capsule, firing the escape system from the pad, which is the test that proves you can get a crew off a rocket that is about to fail on the ground, an integrated landing and takeoff test of the lander, tethered ignition tests of the launch vehicle's engines, and then, on the 10th and 11th of February this year, a low-altitude flight demonstration from Wenchang, a Long March. 10 demonstration vehicle carrying an uncrewed Mengzhou lifted off, and the capsule separated and executed an abort at the point of maximum aerodynamic pressure during ascent. Max Q, as it is usually called, the moment when the forces on the vehicle are at their highest and an escape is hardest. That is the difficult abort test, and it worked. A booster was also recovered at sea. The forward schedule as publicly described runs: an uncrewed orbital test flight of the crew capsule late this year, docking with the Chinese space station to verify systems and return. The lander's first flight in 2027, a joint test mission in 2028 or 2029, and a first crew roughly a year after that. Put both timelines side by side, and the honest conclusion is unglamorous. Neither is imminent. Both have slipped. Both are years away from putting a person on the lunar surface, and both depend on hardware that has not yet flown in the configuration it needs to fly in. Which is exactly why I keep insisting that this is not the race to watch. The robotic mission launching in the next couple of weeks will produce its result long before either crew program reaches the surface, and what it finds will constrain what both of them can do when they get there. If the water is abundant and accessible, both architectures get easier, and the case for a permanent presence strengthens for everybody. If it is scarce or locked up, then both programs are heading for a destination that does not deliver what its selection assumed, and the country that finds out first has years of advantage in adjusting. The measurement precedes the landing. It always was going to. We have simply been looking at the landing. There is a general lesson buried in that, and it applies well beyond spaceflight. The decisions that determine what is possible are almost never the ones that get covered, because they are made early, they are technical, and they do not photograph well. The coverage arrives later at the moment of visible drama, by which point the actual constraints were locked in years earlier by a funding decision nobody reported. Part 12. Who gets to say what is theirs? There is a question sitting underneath this whole story that people ask constantly and that deserves a direct answer. If someone gets there first, do they own it? No. Landing on the moon confers no ownership of the moon under any framework currently in force, and no announced mission by any country claims otherwise. A flag is a flag. It is not a deed. That said, I'm not going to pretend the legal picture is tidier than it is. There is a real and unresolved tension in international space law between the principle that celestial bodies are not subject to national appropriation and the increasingly detailed frameworks countries have developed for extracting and using resources found on them. Those two things are not obviously compatible, and different states read the balance differently. It is a live debate among serious lawyers, not a fringe concern, and it has not been settled by anybody. But whatever the resolution, it will not be settled by who lands first. What first access actually confers is something more practical, and I would argue more valuable in the near term. Knowledge, where the resource is, what form it takes, how hard it is to reach, and the head start that comes from knowing before anybody else does. That is the real prize in this story, and it is the reason a robotic prospecting mission matters more than a crewed landing. Now let me address directly the alternative explanations that circulate around all of this, because they are widespread, and because I think the audience deserves to have them taken seriously rather than waved off. The strongest version goes like this: the cancellations were not about money. NASA already knows what is at the lunar South Pole, and the missions were killed to control what gets found and who finds it. I understand the intuition. A finished rover that does not fly is genuinely strange, and strange things invite explanation. But look at what this particular decision actually generated. A review board finding written down that assessed a module's schedule at 0% and criticised the program's engineering culture in the process. Budget proposal language, published, naming escalating costs as grounds for termination. A stop work order. letters from congressional committee leaders demanding answers about why a mission was cancelled, and a public layoff announcement at a supplier in Arizona. Concealment operations do not produce that much paperwork. They especially do not produce irritated legislators writing letters that get published. What this record looks like is not a secret being kept. It looks like an argument being had in public by people who disagreed with each other, which is the ordinary condition of a large government program. The second claim is that something is already down there, that the intensity of interest in a few square kilometers of crater floor is itself the evidence. I will concede the premise completely. The interest is real, it is intense, and the convergence of multiple national programs on the same small patch of terrain does look peculiar if you do not know why. The simpler explanation is the one this entire video has been building. Those craters are among the only places in the inner solar system where volatile compounds survive at the surface indefinitely. Everywhere else, they are stripped away. If you want water without hauling it up a gravity well, that terrain is where it is, and there is no alternative site to choose. The concentration of missions reflects a concentration of physics. Everybody went to the same place because the moon only has one such place. The third claim is that the whole competition is theatre, staged to justify budgets. That one struggles against the evidence more than the others, because the American side has just cancelled 2 major programs and dispersed the workforce building a third. 70 people in Tucson did not lose their jobs as part of a budget justification exercise. Cancellation is the precise opposite of what the theory predicts, and when a theory predicts the opposite of what happened, the theory is the thing that needs revising. So let me bring all of it back to where we started. We know that hydrogen is concentrated at the lunar poles because multiple independent instruments from multiple countries have measured it over more than 2 decades. We know that something water-like sits inside the permanently shadowed craters because in 2009 we threw a rocket stage at one of them and photographed what came up, and what came up contained roughly 155 kilograms of water. And we do not know how much is there. We do not know how deep it sits. We do not know what physical form it takes, or what it is mixed with, or whether any machine human beings are currently capable of building could actually get it out of the ground. $20 billion, a crude program, a commercial industry, and the entire premise of a permanent human presence beyond this planet are balanced on that one unmeasured quantity. And the country that committed the $20 billion built 2 separate missions to go and measure it, and stopped both of them. For the whole of human history, the moon has been a thing to look at. For 3.5 years at the end of the 1960s and the start of the 1970s, it was a thing to visit. Whether it becomes a thing to live on is not going to be decided by a rocket, or a flag, or a landing date, or any of the moments that will get the coverage. It is going to be decided by a quantity of ice in a hole that has been dark since before anything on Earth had a spine. In a matter of days, if the schedule holds, a rocket lifts off from an island in the South China Sea. Some weeks after that, a lander touches down on a sunlit ridge at the bottom of the moon, and at some point after that, a small machine will lift off that ridge on thrusters, cross a line between light and permanent darkness, and go down into terrain where nothing built by human hands has ever operated, to ask the ground a question nobody has ever asked it directly. It has to get there, it has to survive, and it has to come back with a number that means something. Whatever that number turns out to be, it will arrive quietly, in a technical release, and it will reset the terms of every plan any of us have made for the next 50 years. So here is the thing I keep turning over, and I would genuinely like to know what you make of it. What happens if it comes back low?